All right. So today we will talk about AES, which is actually the main standard for block encryption after DES. And so we'll talk about how this one works, what is the structure, what is the round function, expansion, and decryption. Now this is actually what you would call the latest encryption technology, and DES was designed in 70s, AES was designed in 90s, late 90s. So published in 2001 by NIST, and just like the previous one, there was a competition which was won by scientists from Belgium. So Rijman and Demon, they had an algorithm called Rizendale, which became AES after winning over 21 other competitions or 21 other proposals. Now this algorithm is much more general than AES. It allows many block sizes and many key sizes, but AES restricts it to one block size, 128 bits. This is 16 bytes. It does allow multiple key sizes. So you have AES 128, AES 192, AES 256, and I think the list goes on. Basically, so whenever somebody says AES, that is the key size and the number. That is the key size. The block size in all these cases is 16 bytes. So the block size does not change. And it does not use the previous Feistel structure either. Yeah, go ahead.
Is there some benefit to fixing the block size to 128 bits?
So there must be something about that. However, all that is not documented. Some of these things are not documented. So we don't know why they don't allow 192 and 256. So I don't know, for example. And it's not in the book. It is not. I mean, so some of these things, so for example, when we go to the round function, just like we went into DES, there are some tables. However, the tables are prepared is not documented. Although, we know that they're nonlinear and so on and so forth. So some of the common mistakes are avoided. So why they don't want to bigger block size for a bigger key size, I don't know. All right. But it doesn't use the previous DES structure. So it doesn't use Feistel, which means that it uses both the complete 16 bytes in every round. In Feistel structure, if you remember, we divided into two pieces. The right one was done first, and then the left became right, and then it was done in the second round. And third thing, it doesn't use any bit operations. It is mostly byte operations. So that makes it software friendly. DES was designed for hardware, and it was easy to move 56th bit to 23rd bit and all that. We don't do such things here in AES. So those are the main differences. The main structure is as shown here. Basically, first of all, the number of rounds is not fixed. Number of rounds depends upon what the key size. And actually, in case of Rizendale, it also depended upon the block size. So if you have NB as a number of blocks, where number of words in the block, which meant that 32-bit words in the block. So right now we have 128-bit words, right? So we have 4 32-bit words. So NB is 4 right now fixed by AES. NK is 32-bit words in the key. So in 128 that would be 4, NK would be 4. In 192 that would be 6, and 256 that would be 8. So the number of rounds is 6 plus max of NB comma NK. And if you calculate that for AES 128, there are 10 rounds, 192 12 rounds, and 256 14 rounds. Now you ask the question, is there advantage to fixing it to 128? I mean, obviously the originators didn't think that, so they allow you to have different sizes, but NIST restricted it to 128 bit. So I don't know as to why they restricted it to 128 bit. But the original people allow you different block sizes. All right. So anyway, so you have 10, 12, and 14 rounds. All the rounds are identical except for the last one. So if you have, let's say, 10 rounds, 9 of the rounds will consist of 4 steps: sub, bytes, shift rows, mix columns, add round key, and then you go back. The last one has sub, bytes, shift rows, add round key. There is no mix column in the last one. Now again, I have no idea as to why they did that one. But again, this is the design of the original AES, Rizendale as well. All right. So as before, substitution is done. Substitution is done so that there is a lot more diffusion, and then the mix column is what we call transposition. Actually, in this case, mix column is also a substitution. Shift rows is more like a transposition, so that is done for confusion and all that. So based upon that kind of technology, that kind of thinking, substitute bytes. So you take the original information, which is written like this, and it is written column wise. So your message is EA835CF0044523 and so on and so forth. First column first. And so you take in this case, in case of 128, it will always be a 4 by 4 because you have 16 bytes. Each of these is 1 byte. So you take any byte and you take the nibble, first nibble, half byte. That becomes the row number, and the second nibble becomes the column number, and then you find the substitute. All right. So basically, it is showing that x, y would be substituted by this one. So you do EA, and you will find out that it should translate to 87. 83 will translate to AEC and so on and so forth. There is a whole 16 by 16 table in the book. All right. Any question about this substitution? It's straightforward. In any software or hardware implementation, this is built in. Second thing is shift rows. Actually, this would probably call it rotate rows in my views. But anyway, what they do is they rotate the rows by one entry or one word. Sorry, one byte. Sorry, 1 byte. So the first row doesn't change. The second row goes by 1 byte. So the first byte becomes the last one, and the second one becomes the first one, and so on and so forth. The second row rotates by 2 bytes, and the third row rotates by 3 bytes. So in this case, you can see the first row is same, second row you just change 1 byte around. Third one is mix column, and this is where this Galois field comes in. So this is where multiplication is done, a matrix multiplication is done in Galois field 2 raised to 8 using this polynomial. And this is why we had the whole lecture prior to this about Galois fields, is that when we say number 02, we really mean here 02 is what polynomial? Can anybody remember the polynomial for 02? How will you translate that to a polynomial, 02 to a polynomial? Make a binary expansion and then write down the polynomial. What is the binary expansion of 2? 1, 0. And therefore that is x plus 1. What is 03? What polynomial is that? Sorry, 10 is not x plus 1. 10 is x. I was wrong. 10 is simply x. 03 is x plus 1. Right. 01 is just 1. And so on and so forth. You put those polynomials here. You put the polynomials corresponding to these bytes there. Multiply them. You get some new polynomials. If they are any more than x8 or equal to x8 term they have, then you subtract that. so that this becomes less than x raised to 8. That is the result you get. All right, so let's just do one example. So this is the matrix for the current state, and this is what we are going to multiply with. So we multiply this with that. So the first row and first column, we take the first row and first column. First row is 0, 2, 0, 3, 0, 1, 0, 1. First column is 87, 6E, 46 and A6. So we multiply 0, 2 with 87, 0, 3 with 6E, 0, 1 with 46, 0, 1 with A6, and then we add together, and we will get 47 by this whole polynomial thing, right? So let's just do that in a polynomial format. First of all, the polynomial itself is 1, 0, 0, 1, 0. So we can do it either in the polynomial using x and all that, or we can just do it in somewhat in binary coefficients only, right? So here I am going to show you an example with binary coefficients only. So the polynomial itself is 1, 1b. You see, this is 9th digit, so 9th bit, so this is 1, then 0, 0, 1, and then 1, 0, 1, 1 is b. So this is 1, 1b. That's the polynomial. Now if you want to do 0, 2 times 87 mod this polynomial, you take 0, 2, which is x, and you take 87, which is this binary value, and you multiply the two together. Since there is only one term here, 1, multiplication is straightforward. All you have to do is shift this whole thing by 1 bit, which will give you 1, 0, 0, 0, 1, 1, 1, 0 at the end. So that is this number here. Now since the first digit or first bit is 1, we do have to subtract. This is x raised to 8 coefficient, so we do have to subtract this number there. So we take this number and we subtract or add, doesn't matter, this number 11b, sorry 11b. So the exclusive OR of these two would give you something which does not have the 9th bit, and that would be 0, 0, 1, 0, 1, 0, 1. Right. Similarly, when you do 0, 3 and 6e, 0, 3 is 1, 1, 6e is this. Now you do this long hand multiplication. In this case, it's not a simple shift. You actually have to have shift and add, right? Because you first multiply by 1, you get the same number. For you multiply the second one, you shift it and then you add, right? You will get this as the number 1, 0, 1, 1, and this is only 8 bit, so this is fine. Right, this is only 8 bits, so there is no more mod to be done. Similar, so you do all that for all the 4 terms. So the first term is this, second term is that we calculated. Third and fourth terms are straightforward, because third and fourth term in the previous example, 4, 6 and A6. All you have to do is just copy them. So this is 4, 6 and this is A6. You exclusive OR all of them and you get this number, which is 4, 7. So this is kind of a most complicated part of everything else was a table lookup. This one is slightly more than table lookup. Although in hardware these multiplications and division are trivial, by the way, because you can make shift registers that will do it straightforward way. All right, so going back to this mixed column thing, mixed column is a Galois field matrix multiplication. These are all polynomials. You write your own terms as a polynomial, multiply them, whatever result you get, mod this polynomial You write that down here. Everybody feels comfortable being able to do that? Mix columns? All right. The third or fourth step is add round key. And that's straightforward. You take your state, you take your key. Key itself is 128 bit, so that's very straightforward. With 192, it's a little bit complicated, but for 128 bit, you have 4 by 4 here and 4 by 4 here. Just take bit by bit exclusive OR. The next thing is, so we go back to the previous example here. So we know how to do substitute byte. That was simply a 16 by 16 matrix. Shift rows was simply a rotation of the rows. Mix column was that matrix multiplication. Add round key is simple exclusive OR. So we understand this. The main thing is, how do you get the round key? Right? Everything else is explained. The only thing we haven't explained is how do you get the round key. The round key, again, the algorithm depends upon the key size, and we'll explain it for 128 bit because it is kind of complicated for other sizes. So for 128 bit, you divide that into 4 32-bit words, and so the first subkey is simply W3, W2, W1, W0, which means whatever you selected 128 bit, that is your first round key. Okay. Now, for the other rounds, we somehow use these 4 32-bit words. By the way, you should notice here that if I gave you the key, or if somebody gave you the key, you write down the column first. So the first column will become one word, second column will become second word, third column will become third word, fourth column will become fourth word. Then, if it is not a multiple of 4, so round number 1, 2, 3, 5, 6, 7, 9, 10, 11, 13, 14, 15, if there is a 15th round, they use this formula. All you do is exclusive or I minus 1 with I plus I minus 4, those words, and you get ith word. So you take one column exclusive or with some other column, and you get the new column value. Sorry, no, I'm sorry, this is for every round. I'm sorry, it is not the K, I is not the round number. Basically, this is for the words which are not multiple of 4. For the words which is multiple of 4, then you do this. Actually, it also becomes a round number because basically in every round you have 4 words, and if you keep writing them, you know, they will become the keys for the first round, second round, third round, fourth round, and so on and so forth. So it works out same way. So anyway, so for which were multiple of 4, so the word number 4, 8 is just the word number 4, 8, 12, and so on and so forth. They are done by 3 steps. First, you rotate the k minus 1 by left 1 byte. Then you use the sub byte functions to all 4 byte, and the sub byte function is this function which was shown before. This function. You apply it to the keys also. Then you do exclusive OR with 4k minus 4 and a round constant rconc. So that way, there is, just like in DES, they had for every round they had a different number of shift, 1 shift or 2 shift. Similarly here they have a different constant, and so that constant and W4k minus 4, and then the result of these two steps is exclusive OR, and then you get W4K. So now you have words which are just lining up 1, 2, 3, 4, 5. Sorry, the words are 0, 1, 2, 3, 4, 5, 6, 7, and so on and so forth. Keep going. So this is the first round is just that 32-bit, and then the second round would be W4 onwards. So this is how they are calculated. Right, now there is, again, it would be nice to know exactly why each of these steps is, but this is not described in the book or in any place that I have read. Here's an example. So here is the word 0, 1, 2, and 3. This is the 0th column, first column, second column, and third column. This would be written like this: W3, W2. WI, WI plus 1, WI plus 2, WI plus 3. So this is 0, 1, 2, and 3. 0, 1, 2, and 3. Somehow something is missing. This should have 4 words, 4 bytes, W2. So 1 byte is missing here by mistake somehow. Anyway, so if you have 4 bytes in every word, then you rotate the words let's just follow this step. All other words are calculated by exclusive OR except for the W4. So W3 rotated and then substituted, exclusive OR these two, then this is the constant 1. You exclusive OR that constant, and this is what you get, W4. Similarly W, and then here on this side we have D38546. W4K is RSK plus WK minus 4 plus RConc. So K minus 1 and K minus 4. Okay. So we have to exclusive OR that to W0. So if I exclusive OR D3 with 0F, I should get this, DC. I have not verified it. Let's see. D3 and 0F should be at least D right there. Yeah. So there is a D right there. And F is all ones. So 3 complemented would be 6. D3 and F. F is all ones. 3 is all complemented would be 1100. 1100 is 12. C. Okay, so that's correct. So if you take this value Z1 and exclusive OR with W0, you get W4. W5, 6, 7 are just obtained by rotation. And exclusive OR, I mean, as given here. So now let us just see what is the missing word in W2. W2 is right here. 97FE723F. So the last word is 3F. W5 is E9. Exclusive OR with something should give you 3F. So 3F and E9. E and 3. E and 3. E is 1110. E is 14. 3 is 1. So that is, we are going to do W5 and W6 equal to W2. So W2 equal to W6 exclusive OR W5, 6 and 5 equal to E9 and 3F. E9 exclusive OR with 3F. E9. E is 1 1 1 0. 9 is 1 0 0 1. Exclusive OR is 0 1 0 1 1. F is 1 1 1 1. So that gives us 1 1 0 1 and 0 1 1 0. So that gives us D 6. Is this correct so far? D6 would be the last word of W2. So let me just fix that. Okay, anyway. All right. All right, encryption example. So we just saw how to make the keys. Once we have the keys, then the encryption is same thing. We have to do add round, subtract bytes, substitute bytes, shift rows, mix columns, and round key again, right? So first of all, substitute byte is that 16 by 16 table. This is the state before the before the end of the round, before the beginning of the round. So you take 0E, go to the table, you should get AB. Then you shift it. So the first row remains as it is, the second row is shifted, third row is shifted twice, and third row is shifted twice, and the fourth row is shifted 3 times. So that is straightforward. Then mixed column is that multiplication. So this is kind of difficult to get. 16 multiplications will get you that. And then you are ready for the next term. Basically we have 4 steps. Substitute bytes, shift rows, mixed column, and then the add round key. So you just take this value and take that value, and you get the addition, you should get that. So B9 plus 0F, you should get DC, and that should take you to, this is the round key, sorry. You take these two, you should get that. So B9 and 0F should get you 65. This is the state, this is not the state, sorry. This is just the key. The state is here. So these two get you there, and then you do the same thing. So start of the round, this is the state, and this is the key, and the first thing is add round key. So we add 01 and 0F, we get 0E. Then we substitute 0E, we get AB. Then we multiply by the matrix, we get AB. Sorry, no, multiply here. Then we just rotate, and AB remains AB. Then we multiply, we get B9. Then we add the key B9 and 0F, we get 65. Okay? Everybody feels comfortable at least conducting the exercise, finding out as to how the numbers came about? Yeah.
So the round constants, are those set before? Or
yeah, those are fixed. Okay. Those are fixed. So that way there is no confusion. Those are not something that has to be passed on to the receiver. Everybody knows those numbers. And as shown in the previous example here, the round constants were very simple. 0, 1, 0, 2, 0, 4. So, and everything else is 0 there. So round constants are some numbers that were picked to basically for to break the symmetry. All right. So now we want to see whether how good it is. Obviously, it is better than this for sure. But first thing we want to see is how much is the diffusion or what they call avalanche. Avalanche means what? Anybody remembers avalanche from the previous lecture? Yeah? Go ahead. Will change lots of bits. Right. Okay, so that's exactly the point. So here is the one value that we are going to encrypt, and here is the second value that we are going to encrypt. Both of them are identical except for one bit. Like the number of bits that are differing at the beginning of this whole encryption thing is 1 bit. And as we go round by round, at the end of the 10th round, they are differing by 58 bits. Not just half. Half is actually 58, yeah. Half is 64 because this is, here the block size is 128 bit. So half is 64, so close to 64 bits are different. So very good diffusion. Now decryption is basically is not identical to encryption. So you do have to do it slightly differently, and obviously the keys start from here, and so the last key is applied first. That is the reverse order, and then you do it as given here: add round key, inverse substitute byte. So it's not the same thing as substitute bytes. So there is a table which is inverse of the previous table. Inverse shift rows, you shift and rotate in the other direction. Inverse mix columns, you do the multiplication in the reverse direction, and so on and so forth. So these are all inverse functions, as opposed to in this you had the same logic. Only thing you did was the key change, and then you can feed from the top to the bottom. Right? Here not only you do the key change, but also you have to have inverse of these functions. So basically you have to have two logics, encryption logic and decryption logic. All right, so AES actually has been easier for us because we have already finished DES, which had many similar things. The key new things are, first of all, it allows multiple key sizes, and the key sizes keep going up. I mean, I have seen all the way to 3,000 some numbers like that. So the military, etc., they use very strong keys. So 128 bit, 192, 256 bit keys, and depending upon the keys, the number of rounds also goes up. And it's not a fast-tell cipher, so all 128 bits are encrypted in every round. There are 4 steps: substitute bytes, shift the rows, mix the columns, and add round key. And each round last round has only 3 steps, so it doesn't have any mixed columns. And the decryption is not the same as encryption. And the decryption consists of inverse steps. So each step has an inverse function which is used. All right. Any question about AES? Now some of you are very busy in front of your computer, and I kind of wonder what you are busy with. When I'm asking a question about any questions here, is it on your computer, or is it something else going on your computer?
What's that?
Is something else going on in your computer? Please. Okay, so here I think I had asked for you to bring the computer so that we could ask questions, online questions, which I could probably ask. But since we are not asking questions, the computer has really no function right now. And particularly when I want your attention and I see that your attention is not here, that is is not good. So, and also you, sir, the last one. Please pay attention to this one. Okay. All right. Any question about AES? All right, well, if not, then you have to do all these steps. So here is the plain text, here is the key, and so you have to do the add round, substitute byte, shift rows, and mix columns. So as you can see, everything else is very straightforward. Mix columns is a tough one, right? Maybe, I don't know, we can just make it simpler and say not 16 bytes, maybe 4 bytes, right? You can do at least 4 multiplications, not 16 multiplications. So let me just change it to that then. This column, okay? If you do 16, you will really become expert in this thing then. In the exam, it will go like that. So, the more you practice. All right. There is a lab homework, and this is the last lab homework. So far we have just, kind of finished all the 4 steps of hacking. First is to explore, second was to, basic monitor and all that, and then third one is to attack, which we did last time. This one is straightforward. What it is we just want to show you the difference between SSH and Telnet. So we have installed SSH on the machine, and we have installed Telnet as well. Telnet is already installed on every machine. And this actually, probably you can do it on your computer easier as well as on our computer. There is nothing special here. Well, unless you have Wireshark. The thing is, it does need Wireshark. So what we do is you do Telnet and monitor the packet on the Wireshark. Your password goes in clear. Okay? And then you do SSH, and then you can update the password. After doing that exercise, you will probably not be doing any more Telnets anywhere, because that one shows that it's not very safe.